In the early days of coding, we had to hard code rules that would distinguish one class from another. For example, if you've been in machine learning a while, you're probably familiar with the famous iris dataset, which contains information on different types of flowers. In the old days, we would just hard code rules to determine the species of the flower. Say, for example, if the petal size was smaller than 1 centimeter and the sepal length less than 5 centimeters, we can create a rule to classify this as Iris setiza flower. But we've come a long way from there, and now we have machines where we can show a picture of a flower and ask what type of flower this is. In terms of natural language processing, we can build generative models capable of having conversations about flowers, where we could discuss different aspects of the flower and ask the model to identify our flower that way. So, what led to these advancements which now provide us with such powerful models? Large language models are based on a transformer architecture, a type of neural network that was developed by Google Brain researchers in 2017. Transformers are a subset of deep learning. So before we jump into learning about transformers, let's quickly recap what we mean by deep learning. Deep learning is a type of model architecture that can excel at finding patterns in complex data due to its network structure. It begins with input data, such as text or images, and this input is then passed through layers of interconnected neurons, forming a neural network. Each neuron applies a mathematical operation, including adjusting the strength of connections or weights between the neurons. These weights are continually updated during a training phase to minimize the difference between the predicted output and the actual output, a process known as optimization. Through iterative adjustments and learning from vast amounts of data, the neural network gradually fine-tunes its weights to make increasingly accurate predictions or classifications, ultimately producing an output that can include anything from text generation and image recognition to complex decision-making, classification, and problem-solving. Different types of neural networks have been built to excel at different types of problems. For example, convolutional neural networks are designed to mimic the way the human brain processes vision, and so these models excel at vision classification tasks. Neural networks seem to do pretty well at analyzing images, but often still struggle to analyze language. Before transformers, the best thing we had for language was recurrent neural networks. Let's say we want to translate a sentence from English to French. A recurrent neural network would take one word of the input sequence at a time, process it, and then sequentially give the translated output one word at a time. The sequential aspect of this process is important. If you shuffle words around in a sentence, you can often change the meaning of the sentence or remove any meaning from it whatsoever. So being able to preserve the word order by dealing with words sequentially is important. But recurrent neural networks really struggled when the input text was long, such as an entire essay. Once they get towards the end of the piece of text, they'd forgotten what had been said at the beginning. This is a real problem, as it will miss important context from earlier in the text that may be important throughout the whole input. For our language models to work effectively, they need to have some sort of memory of what was said earlier in the text. Take, for example, the following sentence. The New York Times is a daily newspaper. It was first issued in 1851. In the second sentence, it refers to the New York Times from the first sentence. But we would only know this if we were able to keep in memory what was mentioned in the first sentence. If we were only able to look at each token at a time, or tokens that are very close to each other, then we would not be able to truly understand the meaning of the second it, and thus the meaning of the whole text may be lost or misunderstood. By also processing words sequentially, it means that recurrent neural networks couldn't parallelize well. If we break up a piece of text to run in parallel, the recurrent neural network has no way of passing important contextual information within the text between itself. This means that training would often take a very long period of time, and it limited the size of the datasets that could be used for training. Recurrent neural networks would not be able to handle the size of the training data we see used for large language models today. It would just take too long. This is where transformers come in. Not only do transformers work in such a way that we can utilize parallelization, but they also have a novel way of being able to pay attention to the most important words in the text required for context. This means that transformer models can have a superior understanding of contextual information in the text. You might notice I said that transformer models are able to pay attention to the most important words in a piece of text. Attention is the name given to the technique that allows the transformer to pay attention to specific words. Let's now move on to our next lesson, where we cover attention in more detail and see how it's enabled the incredible language models we see today. In 2017, a paper was released titled "Attention is All You Need," where the researchers introduced the concept of transformers along with the attention mechanism that formed a fundamental part of these models. The attention mechanism enables a model to weigh the importance of different words or tokens in an input sequence when producing an output. The key idea behind attention is that instead of processing the entire input sequence at once in a fixed manner, the model can selectively attend to relevant parts of the sequence at each step of processing. This is achieved by assigning a weight or an attention score to each token in the input sequence. Tokens with higher attention scores are considered more important for the current step, and the model uses these scores to compute a weighted sum of the input tokens. This weighted sum is then used to generate the output. This mechanism is what enables transformers to manage long-range dependencies in data. It's fundamentally a weighting scheme that allows a model to focus on different parts of the input when producing the output. The paper gives an example of the importance of attention during language translation. Suppose we want to translate the following phrase from French to English. A simple translation model could take each word in the text and translate it to English each token at a time. However, this would be incorrect, as the order of words in French versus English differs. So the following phrase would be translated to area economic European rather than the correct version in English, which would be European economic area. A simple word-to-word translation is not good enough. We also need to be able to look at or pay attention to other words in the text. This chart is from the 2017 paper, and it shows which words are being paid attention to during translation. You can see that it's not a simple one-to-one relationship. Relevant tokens are being paid attention to at each point to ensure the correct translation. When dealing with transformers, you'll also hear the phrase self-attention. Self-attention is a term for a specific type of attention mechanism that computes relationships within a single input sequence, allowing the model to capture contextual information and dependencies between input elements effectively. So, now we have an idea of how powerful transformers can be, let's take a deeper look into their architecture. This diagram gives an overview of the transformer architecture. This can look quite complicated at first, but we're going to go through each step and break it down so you can understand what's going on before we start using these transformers ourselves. Let's think back to our example of translating between French and English. If we chose to use an RNN, a recurrent neural network model for this, each word would be passed as an input one at a time. In a transformer, however, we're able to feed all the input words into our model at once and deal with them simultaneously. This is such a powerful aspect of transformers. But how is it possible? The transformer uses an encoder decoder architecture, which we'll go through in more detail now. Let's first look to the encoder block and see what's going on there. The first step in a transformer's architecture is creating the input embeddings. If you're familiar with natural language processing, you'll know that we can't feed text directly into a model. We need to first convert it into a numerical representation. Let's go through the process of creating these input embeddings together. The first step is to break down the input text into tokens. So if you're not familiar with tokens, these can be words or subwords or even characters of the text, depending on the specific tokenization strategy used. For example, the sentence, "I love natural language processing," might be tokenized into the following. Each token is then mapped to a unique identifying number based on a predefined vocabulary. This vocabulary is typically built from a large corpus of text and contains all the tokens the model can recognize. For instance, I might be mapped to number 34, love to number 56, and so on. Once tokens are mapped to their respective indices, the model retrieves its pre-trained word embeddings from an embedding matrix. This embedding matrix contains vector representations, often called word embeddings, for each token in the vocabulary. For example, the embedding for I might be a vector like this. These vectors encode semantic and syntactic information about the tokens, because the words that are similar to one another in meaning are mapped close to one another in the vector space. However, the same word can have different meanings depending on how it's used in a sentence. This is where positional encoding comes in. Positional encoding is essentially where we give each token a number, recording the position of the token in the sentence. This means we can keep the information of the order of words within the input data itself, rather than having to deal with one word at a time in sequential order. To ensure that all input sequences have the same length, padding or truncation may also be applied. Padding adds special tokens or zeros to the embeddings of shorter sequences, while truncation removes tokens from longer sequences. This is required for certain models, and we'll look into this later when we get to our practical lessons. The embedding process captures the contextual and semantic information of the input text and represents it in numbers. This is a crucial component in the success of large language models. The resulting input embeddings for all tokens in our input sequence are then fed to the encoder block of the transformer. Once we have our input embeddings and our positional encodings, we're now ready to pass this data onto the encoder block, where it goes through a multi-headed attention layer and a feed-forward layer. One of the core components of the encoder block is the multi-head attention layer. It allows the model to weigh the importance of different tokens. This layer gives us attention vectors that capture contextual information between every token in the text. Let's go through the steps to how these attention vectors are calculated. For each token in the input sequence, we create 3 vectors: a query vector, a key vector, and a value vector. For each token in the input sentence, a query vector is calculated. This query vector represents the tokens in question about the other tokens in the sentence. It's kind of like saying, how much should I pay attention to each of the other tokens? To put it simply, you can think of the query vector as the currently attended to token in the input sequence. The key vectors, on the other hand, hold information about all the other tokens in the sequence. Each key vector corresponds to a different token and contains information that helps determine how much attention should be given to that token. Value vectors are associated with each token in the input sequence. Think of them as information containers that hold the actual content or knowledge about each token. When the query token, the token currently being attended to, asks questions about attending to other tokens, the value vectors provide the answers. The values for these different vectors are what's learnt through training our model. The next step in the process is that we calculate the similarity between each query vector and all key vectors using dot products. This produces a set of similarity scores, one for each token in the sentence, indicating how much attention each token should receive from the currently attended to query token. To ensure numerical stability, we scale the similarity scores by dividing them by the square root of the dimensions of the key vectors. This scaling factor helps control the magnitude of the scores. Next, we apply the softmax function to the scaled similarity scores to obtain an attention weight. The softmax function normalizes the scores so they sum up to 1, effectively turning them into probabilities. So, now we have an attention weight for each token in the sequence, indicating how much attention the query token should give to each other token. We then calculate the weighted sum of the value vectors, using the attention weights. This step aggregates information from the entire input sequence, giving more importance to tokens with higher attention weights. The resulting attention vector represents the combined information from the input sequence, focusing on relevant tokens based on the attention mechanism. We say that this layer of the transformer architecture is multi-headed because transformers will try multiple different iterations of query, key, and value projections, known as heads. Each head learns a different set of weights, allowing the model to focus on different aspects or patterns in the data. The attention vectors from each head are concatenated and transformed to produce the final output of this layer. After the multi-headed attention mechanism, the output is passed through a feed-forward neural network. The feed-forward network learns to capture and model complex, nonlinear relationships within the input sequence. The feed-forward layer in the transformer encoder block is a key component responsible for processing and transforming the information captured during the self-attention mechanism. It's designed to enhance the model's ability to capture complex patterns and relationships within the input sequence. Let's break down what actually happens in this feed-forward layer. The input to this feed-forward layer is the output from the self-attention mechanism. After self-attention, you have a set of context-aware representations for each token in the input sequence. Each of these representations contains information about how the token relates to other tokens in the sequence. The first step in the feed-forward layer involves a linear transformation for each token's representation. This means that a learned weight matrix is applied to each representation, essentially reshaping and projecting it into a new space with potentially higher dimensions. This transformation is usually followed by an activation function, which introduces nonlinearity into the model. Another linear transformation is then applied. This transformation reshapes and projects the data further, often reducing the dimensionality. This step can be seen as compression or simplification of the information. The output of this second linear transformation is the final representation for each token. This representation is more abstract and compact than the input into the feed-forward layer, but it's designed to capture complex patterns and relationships learned during the self-attention step. In summary, the feed-forward layer acts as a set of neural network operations applied independently to each token's representation. It helps the transformer model capture and encode complex, nonlinear relationships between tokens in the input sequence. And because these operations are applied independently to each token, we can run them in parallel, really speeding up the process. Once we've done this, we can move on to the decoder block. The desired outputs we want our model to learn are fed into the decoder block. Think back to our example of French to English translation. The French words would be fed to the encoder block, and we would feed the English words to the decoder block. These outputs go through similar embedding transformations and get their positional encodings before being fed to the decoder block. However, we don't feed all output embeddings to the decoder block at once. They go through the masked multi-head attention layer. This is similar to the multi-head attention layer we saw in the encoder block, but we say it is masked because we need to hide some of the information on the outputs at this stage to make the model learn. We allow the model to see all the French input words. And when I say words, I really mean the intention vectors for these words. But the model will only see the English words that have come before the currently attended to word in the sentence. The model then has to learn what the correct next word would be, rather than just looking at the next word in the given outputs. We call this the masked multi-head attention because words later in the output text are masked or hidden from the model at this point. The multi-headed attention layer in the decoder block receives inputs from both the encoder block and the masked multi-head attention layer. In addition to self-attention, the decoder's multi-head attention also calculates attention scores between the current output token and the encoder outputs. This step helps the model determine which parts of the input sequence are relevant when generating the next token for the output. The encoder outputs are weighted by these attention scores to create a context vector. This context vector represents the relevant information from the input sequence that should be considered when generating the current output token. The feed-forward layer again just makes the output more digestible for the next step in the process. The linear layer is another feed-forward neural network used again to manipulate the output into a useful format. And the softmax layer transforms the output into a probability distribution. This probability distribution is then used to predict the next word in the output sequence. The whole process of this decoder block is repeated for each token in the output sequence, with the previously generated tokens being included as an input for each subsequent step. So there you have it. You now have a good overview of how transformer models work, and we are ready to start using these models.